Assalamu alaikum. A critical part of any network performance evaluation study is the choice of workload. Indeed, it is the workload which provides the context for understanding performance measures. Up till now, we have discussed the importance of metrics and system models for understanding and calculating network performance, but all of that has to be understood in the context of workload. Workload simply means the load being applied to the system that is being tested. And based on the workload, it is possible to have completely different answers. So keeping everything the same, if we change the workload, it is possible to have completely different answers. So it is very important that we first of all realize the importance of workload and then attempt to make the workload as realistic as possible. In other words, we would like the workload to be representative of the actual load that will be applied to the system. Only then can we make some meaningful conclusions from our network performance evaluation study. So to illustrate this and to make this idea more concrete, let's take an everyday example. So imagine you're interested in creating a new store. You want to answer the question that how many salesmen do you require to provide good service? So naively thinking about this problem would lead us to think that the performance is dependent on the swiftness of the salesman. However, while that is true, that the average time the salesman takes to process request is going to be a consideration in calculating the network performance, perhaps a more important concern is what workload is going to be applied. In other words, what is going to be the arrival pattern of customers? How often are they going to come? What is the average number of customers coming in every minute? And also how variable this incoming arrival of customer is. So do they faithfully adhere to the average we've set, or there is a huge variation? Also, is there a deterministic pattern of coming of the customers, or there is burstiness? So burstiness would mean that many customers come at the same time, and there would be extended times in which the salesman is not doing anything, which is a more realistic assumption, because people usually come to such stores in bursts. So because randomness often happens or manifests itself as bursts. So to first of all simplify our calculation, let's consider the simplest case, the most trivial case, in which the customers are coming according to a deterministic schedule. Every customer is separated by every other customer, or the next consecutive customer, by a fixed time, and so on. So to make the example very simple, imagine there is one customer coming every minute. So now if the service time, or the time the salesman takes to process the request, if it is less than 1 minute, we have no problems. No queues would form, because before the next customer comes, the previous customer would be serviced. So in this case, we have no problem of congestion, and you would never have queue build up. But because this is because of our simplifying assumption of the deterministic nature of the arrival. So this deterministic nature of the arrival of customer is actually part of our workload assumption. Now if we change this workload assumption and we keep the average as it was, we keep the average as one customer coming every minute, but we now make it the arrival process as a stochastic process, or we introduce some randomness into it. So now the inter-arrival time is not deterministic or fixed. It is going to vary around the average value. So now as we introduce this variability, we would see that invariably queues would start to form, because now it is not certain that the customers would be always separated by the average inter-arrival time. So it is very much possible that the salesman is currently processing some request and a subsequent customer arrives. In such a case, the subsequently arriving customer has to wait, or in other words, he has to go in a queue and wait for his turn for service. So if the performance of our store in this example has to be good, then the queue should not become unbounded. In other words, the number of people waiting should not keep on increasing. Eventually, you would like the queue to become empty again, and on average, you would like the queue to have, as minimum the number of customers as possible. Good performance would, imply lesser number of waiting customers. So the important point here is that as we increase the amount of variability, the usage of the queue would increase. And now if we imagine that the service time is just a little less than the inter-arrival time. So in this case, now the utilization would be high because we are assuming that the service time is just a little less than the inter-arrival time. In fact, in such a case, you would have, very large queues forming. And this is despite the fact that the average service rate is more than the average incoming arrival rate. In other words, you can actually, on average, process an average customer sooner than the next customer on average arrives. But because of the inherent variation in the arrival process or the inherent variation in the workload that now we have assumed, the process is, the result of the performance is going to completely change. And you would have very large queues forming up. So this illustrates our point that our workload assumption is a very critical factor in producing our network performance results. And every result that we report has to be considered in the context of the workload we are assuming. If the workload we are assuming is not representative of the real load, then you can say that our conclusions are meaningless. So as an example of how such models are used, because we are currently modeling the workload process, we are abstracting the arrival of the customers by an average. We can also give a standard deviation between which measures the variation of the arrival process. So a standard assumption that we make in data networks, which has now been proven to be wrong, is that such arrivals are memoryless. So there are some distributions which we will cover in the later part of this course. There are some distributions which are memoryless, and these distributions lend themselves to mathematical analysis, and they are tractable, they can be easily analyzed. But the unfortunate part is that real arrival processes are not memoryless. In fact, data packets are correlated. They come together, and these bursts actually manifest themselves on many different ranges of time scales. So the Poisson assumption, which indicates that the arrival is independent of each other, the arriving customers do not depend on each other. Even if there is some variation, if you take a large enough time scale, the things are going to average out. So I will now show you a graph in which I will show you the analysis which is based on this assumption. So when we make the Poisson assumption, this is an assumption regarding the workload. And also I'm going to show you something that has been empirically observed. So in this graph you can see that the analysis which is based on the simplistic workload assumption that the arrival processes are Poisson distributed actually gives us better results. And in fact, the actual results are more serious. They indicate that on lower levels of utilization, you would have higher delay. So this has a lot of impact on our network performance evaluation. In later part of this course, we are going to study, what are some realistic workload assumptions that we must make about data networks. We will also see why Poisson approximation, or the workload assumption that the arrival processes are represented by Poisson distribution, or inter-arrival time is represented by exponential distribution. These are often, they do not add up in reality. So because of that, we have actual network performance not being in sync with what we would predict. So this highlights the importance of workload and why it's important for network performance evaluation study. Let me now outline the remainder of this session. I'm going to initially talk about workload and system models. Up till now, we have studied modeling, but only in the context of modeling systems. Now we would be extending the same concept to study the workload. How are users coming? What is the arrival, arrival distribution? What is the inter-arrival distribution? What more can we say about the workload? In the second part of today's session, I'm going to talk about distribution fitting, which means given some data, what can we infer about the parent distribution from which we hypothesize that this data is drawn from. So we are trying to figure out what is the parent distribution from which the measurements are being drawn. Lastly, I'm going to talk about, having made this prediction about what is the parent distribution, how can we determine if actually our prediction is good? So this is done by performing goodness of fit tests. So we compare the distribution, the one which we have predicted and the one which we observe empirically. We compare them and see how good a fit is. So let's start with the first part, in which I'm going to talk about workload and system modeling. So up till now, we have talked of modeling, and we've talked about modeling as a process of abstraction, a process of simplification and generalization, in which we attempt to remove all the extraneous details and at the same time include all the essential details. And the definition of extraneous and essential would be according to the task that you are doing. So if you are modeling, let's say, the effect of buffers on performance, then everything related to this has to be modeled. But if you are performing analysis for some other thing, it might not be very important to model the buffers and everything related to it in detail. The process of modeling is fundamental to the scientific method. We've seen how hypotheses are basically abstractions of reality, which can be checked against empirical observation. So we make a hypothesis, we make predictions on the basis of this, and then we compare. So the scientific method actually depends a lot on modeling. However, we would now see that in fact modeling is not unique to science only. In fact, the general idea applies to art as well. And I'm now going to borrow a figure from the book Understanding Comics by Scott McCloud, who illustrates that the idea of generalization, of modeling, of abstraction applies to a lot many fields. And because of this wide applicability, we are going to read and see what he says and try to understand in the context of network performance evaluation. So he indicates that for his job, which is drawing comics, the process of abstraction is very fundamental. And in certain cases, when he wants to draw something, he wants to make it as generic as possible so that it reflects the average man. In fact, every man can see himself in it. So if you see the slide now, the rightmost face figure is very abstract and it is very general. You have removed all the extraneous details and it represents the face of almost every man. But if you go to the other extreme, you would see that there is a lot of specificness there. There is a lot of detail. and that makes this face particular to one man. So the abstraction ladder to models can be seen in the diversity shown here. So on one end you have complexity and a lot of details. On the other hand, you have simplification and removal of everything that is extraneous. You can also compare realistic models versus iconic models, in which iconic models have a lot of details removed. And you also can think of exact models and approximate models. When something is exact, it is then very much focused on the thing being modeled. But if we want to make things more general, we would make it a little more approximate, in which we take out all the details which are unique to this thing, and we make it more general. In terms of workload, you can think of generalizing from trace data. So you receive some measurements, and from that you want to make a model of the workload. So any sample or any trace actually has a systematic component and also a random component. We've discussed this before, that if you keep on drawing samples, every time you're going to get something different. So now if we model our impression of the population just on the basis of this sample, we would then be overfitting, because we will not only be modeling the systematic behavior of this sample, but also the random behavior of this sample. So it's important that we do not model too deeply. So we just focus on the general characteristics so that we can generalize. The purpose of a model is to generalize. So an important quote which I think is relevant here is that the essence of modeling, as opposed to just observing and recording, is one of abstraction. This means two things: generalization and simplification. I think this captures the idea very well. When we are trying to make models, we should try to focus on the invariants, something that we expect to remain the same as we keep on checking more traces, as we keep on making and taking more samples. We would expect the systematic component to remain the same, and we would expect some random variation. So our model should try to capture the systematic component. In other words, we should focus on the invariants. When we are going to study internet measurement in the later part of this course, we're going to mention some invariants when we come to model the internet. The internet is notorious for being very complex. In fact, it has been shown that it is a very hard thing to model. In fact, this is a moving target, because every time with the passage of time, the internet evolves itself. So any model that you make is going to become outdated very soon. So now, how do we then cope with this? The idea is that you try to find out the invariants, the things which are remaining constant, and your model should be based on that. Because if you try to capture the very recent trends, the ephemeral trends, those trends are going to go away. So then you risk the chance of having an outdated model. It's very important that we focus on the invariants for incorporating in our model. So a workload has some static attributes and some dynamic attributes. And one of the fundamental challenges in building a realistic network performance evaluation workload is that we have to model the dynamic attributes of the workload. And these dynamic attributes are difficult to model. In network performance evaluation studies, the distributions that we get are often difficult to work with. They are not the usual mild kind of distributions. In fact, the recent trend is moving from such distributions to model the workload to distributions that allow for wild behavior or extreme deviations from the mean. We would cover these distributions later on in this course, but I want to convey now that the dynamic attributes such as the inter-arrival time, the number of counts of incoming request, the job size, you can imagine the file size on a web server, and this thing is going to change with time. So every attribute that changes with time would be called a dynamic workload attribute. And it's important that we do not only capture the static attributes, but also the dynamic attributes. And in fact, the usefulness of your study or the overall success of your study would depend on how well you have modeled the dynamic attributes of your workload. Having then formed a workload model, how do we go about working with such a model? The idea is that once you have a model, which may be a distribution, a mathematical distribution, which may be a theoretical distribution or an empirical distribution, nonetheless, you have an idea about what values are likely. And then you can sample from this distribution. And this is how workload works. You make a distribution and then you draw out samples from that distribution. So every time you take a sample, you're going to have something different. But the statistical properties of this sample would still remain consistent. So let me now tell you about different kinds of workload models. The most basic kind is to use actual real data and then use it for driving your simulation or your network performance evaluation studies. The drawback with such an approach is that while this trace data captures the systematic portion of the system being modeled, but it is quite possible that it may also have some random error. So if we are going to base our network performance evaluation study on this trace only, then the efficacy of our results would depend solely on how representative this trace is. Another drawback with using trace file approach to performing network performance evaluation is that you are limited to the data range that was seen in the trace file during the observation period. Now, the thing is that when we do such a thing, we are confining ourselves to only repeat history. But history rarely repeats itself. And in network performance evaluation study, it never repeats itself exactly. So if we are going to base our network performance evaluation study on some past history, this may not be a very good way of doing analysis. So one way in which we can remove or avoid these errors or issues with traces is that we can use distributions, which are abstractions of trace files. So while trace files are the most, in a sense, the most real workload measure, but as mentioned before, it also has some random component and it may not be representative of the actual workload. So we try to capture the systematic component of this trace file, and we can do it by either equating the distribution of the workload to a theoretical distribution. If we can eyeball the data and we can immediately see that it looks like this data has come from this theoretical distribution, then we can actually make a theoretical workload model. There may also be some basis for doing this by knowing the mechanics of what is being modeled. So if something is likely to be modeled by an exponential distribution and we already know it by knowing the system, we can actually try to fit the exponential distribution to data and see if there is a good match. And if there is a good match, we can abstract away the workload and represent it by the ideal exponential distribution. In many cases, the empirical distribution of data does not match exactly or even approximately with some theoretical distribution. And then we are in a quandary if we should use the trace file or we should abstract the trace file into some empirical distribution. So let me differentiate these ideas. In a trace file, you have only the data that you recorded. When we talk of an empirical distribution, we try to abstract the data that we have into a distribution function which will give us data which is statistically similar to the data in the trace file. So this is like a compromise between using a trace and a theoretical distribution. So it really depends on the kind of data that we have in a trace file, and then it is determined what kind of a workload model suits best. Some of the questions that we must ask ourselves when we are trying to determine the best workload model is how much details do we want to incorporate. Also, how representative the workload model is. Lastly, how timeless the model is. And all these three questions are important to address. So if we want to abstract and remove as much details as possible, we can consider the usage of some distribution, because a distribution is a very concise way of representing the data. We can also talk of how representative the data workload model is of the actual workload. So a trace file is representative only of the observation period. It may or may not be representative of the actual general workload. So we are not really sure if the insights that we get from the trace file can be generalized beyond the observation period. When we are talking of a distribution function, it gives a generic fit to the observation period of the trace file, and we hope that it extends beyond that observation period as well. When we talk of the timelessness of the workload model, we are interested in building a model which does not become outdated very soon. And this is a real problem in network performance studies, because the internet is evolving at a very rapid pace. So workload models that were created only 2 or 3 years ago are now being outdated. So for example, the World Wide Web is evolving. Earlier you had a different kind of a World Wide Web, Web 1.0, now you have Web 2.0, and you have even newer ideas being incorporated into the modern World Wide Web. So the idea is that you try to search for the invariants, and you try to keep and incorporate features that you expect will not become outdated very soon. Okay, now let's talk about different kinds of workload models in respect on what they are attempting to model. So the first kind I'm going to talk about is called descriptive modeling. It is also called black box modeling, in which you're trying to fit a distribution to the observed data, irrespective of how that data was actually created. So in a sense, this is only modeling the data that was observed. So you can see on the slide here that you have a system in use, and you monitor and you produce trace files from that. And from the trace data, you perform statistical analysis, and you abstract the data that you have into some statistical model, and that now represents the data that you got from the trace file. So this is a descriptive model, in that it is actually trying to model the data. It is not trying to capture the intricacies or the essence of the processes that created this data. So having created this model, you have a distribution, and then you can sample from this distribution to get some more data which has similar statistical properties to the data that you had in the trace file. Another kind of an approach to building workload models is known as generative or constructive modeling, also known as white box modeling, in which we are not trying to model the data per se. We are trying to model the processes which created the data. So we would be, for example, modeling the system which led to the creation of this data. We would be modeling the user behavior and interaction which led to the creation of this data. And this is a more powerful way of looking at workload data. In many cases, you also have a hybrid of these two approaches, a white box approach and a black box approach. So it really depends on the kind of study that you're performing, and you should explore both these methods, and you should know that the white box method is a more general method, and the insights that you gain from a white box modeling exercise is expected to be stronger than the insight that you would get from an effort in black box modeling. The data created from such models is called a synthetic workload, because this is not a real workload. In fact, what you've done is, if you created a model of the real workload, and from that model you have created a sample. The benefits of using a synthetic approach to modeling the workload is numerous. And one of the most important benefit is that you can make repeatable experiments. So it's very hard to have a real workload repeat exactly as it was, and even more difficult to change it in a controlled manner. However, if you're using a workload model, a synthetic workload model, you can do this very easily. You can also generalize and avoid noise if we are using synthetic workloads, because we are generalizing from the data to capture the systematic components of the data. And in this way, we avoid being focused too much on the trace data. In other words, we avoid overfitting the data. So this is very important, and a very important benefit of having synthetic workloads. Also, when we abstract the trace data usually is a lot of data. And if you try to just eyeball that or inspect that, it is very difficult to get an insight about the system just by observing the trace data. However, if you can abstract the trace data into some model, it also helps you to form a mental model of how things are working. This is especially true if you're using constructive modeling, in which you are modeling the processes which created the data. So a benefit of using synthetic workload would also be that it aids in better understanding. Lastly, it is more efficient because it gives us a very concise way of expressing the characteristics of the workload. If we are doing trace-based analysis, then we are limited in many respects. For one, we cannot use trace file data with analytical models. Analytical models are mathematical models which can give us very quick insights into how systems work. How would the system behave if we change some aspect of the system? So for that, we need a mathematical model for the workload as well. So trace files would not work with analytical models. Also, because of its conciseness, you actually do not have to deal with trace files that can be of very large sizes. So this concludes the first part of this session. We can now start the second part of this session, in which I'm going to talk about distribution fitting, or trying to capture the parent distribution from which the sample, the trace file data that you have is drawn from. So when we talk of distribution fitting, initially we're going to talk about what is the most appropriate distribution for the data that we have. And we can do this by using our intuition, our judgment, or by inspecting the data and trying to see where it comes from. And then once we know the distribution, especially if we're talking of a theoretical distribution, in most cases we also have the additional problem of estimating the parameters of the distribution. And then once we have estimated the parameter of the distribution, now we know what distribution is a model for our data, and then we can do a goodness of fit test to see how the distribution that we've built matches the empirical data observations. So For estimating the input distribution, often the first thing that we should do is just to graphically draw the data that we have. So we can draw the data in the form of a histogram, and we can see 4 histograms here. And if we get such histograms from our data, we can immediately make a connection. So for example, the top right distribution looks like an exponential distribution. So just by observing the histogram, we get some intuition, or we can make a judgment about what distribution should we be comparing against. Also, an added benefit of using such a graphical approach is that you can eliminate many candidate distributions, especially if we take into consideration the range of the values. For example, in a normal distribution, you can have negative values as well. So if you have data that is never going to have a negative value because you already know it, you know the system so much, then you can exclude the possibility of fitting your data to a normal distribution. We can similarly extrapolate this to other distributions. If you have, for example, the gamma distribution, and we're going to study these distributions later on in this course in much detail, but a gamma distribution does not have an upper bound. So we cannot use a gamma distribution to estimate the proportion of something, because in that case your value will not be more than 1. But here the gamma distribution can take a larger value. You can also differentiate between a heavy tail distribution and a light tail distribution. So if you have data that has some very extreme outliers, some data that is very far away from the average of the distribution, then you should consider using a distribution which has longer or a heavier tail. So for example, you might consider a Pareto distribution. So we will cover this in the later part of this course, but I bring this now to illustrate how just simply visualizing the histogram can give you hints about what distribution is most relevant. Also, you can eliminate many candidate distributions. Having decided on some eligible distributions, then you have the question of finding the appropriate parameters of those distributions. As mentioned before, most of the theoretical distributions are abstractions of reality. So they are approximations of what you would expect if you conducted the experiment many times, or you took a large enough sample. So you can see on this slide a uniform distribution model and what you would expect when you actually sample from a uniform distribution model. The empirical model is almost always a little different from the ideal model. This is because of the random variation in the sampling process, and also because the theoretical distribution is an ideal distribution. In some cases, it's theoretically impossible to have the exact match of the theoretical distribution and the empirical distribution. Now, once we have decided on the distribution that we want to check for its fitness, how appropriate it is for fitting to data, then we have the question of parameter estimation. For example, in a normal distribution, you have 2 parameters, the mean and the standard deviation, or also alternatively the variance. Both of them are interchangeable, can be calculated from each other. You can also think of a Poisson distribution. A Poisson distribution or a normal distribution is a distribution from a family of distributions, and this family is distinguished by the parameter it uses. As an example, family of normal distribution is an infinitely large family. For every value of mu, you have a different normal distribution. So it's important not only to specify what your distribution is, but also to specify what your parameter is. So the question of parameter estimation is simple for the simple distributions, because the exponential distribution, the Poisson distribution have only a single parameter, but other distributions have more parameters. So we will not get into the details of how to estimate parameters, but this is something that we need to do. And the last thing is, if you cannot match your actual data exactly to some theoretical distribution, you can form an empirical distribution. And let's see an example of how that may be done. So we see some data here. So we have 10 data values, and we are asked to plot the empirical cumulative distribution function of this variable. So what we can do is, we assume that this does not match to any theoretical distribution. So we can then draw an empirical distribution, and that's easily done by plotting the x values on the x-axis and then incrementing by 1/10 for each value. On the y-axis, you are showing the probability of having a value of the random variable having a value equal or less than the x value. So the lowest value that we have in this range is 0.71. So at 0.71, the ECDF, the y-axis makes a shift from 0 to 0.1, which means one of the 10 values is equal or less than 0.71. Similarly, if we talk of 41.82, it has distribution function value of 1, which means all of the values are less or equal to this value. So in this way, we get an empirical distribution function which helps us abstract the data that we have. And then we can draw samples from this distribution. And every sample that we draw from this distribution is going to have similar statistical properties if we sample long enough. So let's now talk of the third part of today's session, which is, having determined the appropriate distribution, how do we measure how good the fit is to actual data? And to illustrate that, let me first of all show you how goodness of fit works. So the real world process is sampled, it is measured, and it gives us certain data. And we represent that in a trace file. Also, we have a hypothesis, and on the basis of this hypothesis, we hypothesize that the data is from this parent distribution, and we form a statistical model on the basis of that. In other words, we are saying that the data that we have is actually a sample from some distribution, and we have estimated that that distribution is what we have predicted. Now we want to compare the distribution that we have predicted, and we want to see if the observation actually match with what we would expect from this distribution. So this can be seen as the title of goodness of fit testing, which is shown on the slide. You're comparing the data and the statistical model, and you're trying to determine how good of a fit there is between these two distributions. Let us now try to capture the essence of the goodness of fit test. What we're trying to do is, we are trying to compare two distributions, and if the deviations between these two distributions is large, we would say that the distributions do not fit to each other. But if the distribution is not having a lot of deviation, the mutual deviation is less, then we would say that we cannot reject that these two distributions are similar. So we can see this on the slide now. You have the empirical distribution shown in the form of a histogram, in which the bin values actually represent certain interval, and you are trying to see what distribution matches it. So for the histogram shown, we are trying to see if an exponential distribution is a good fit to this data or a log normal distribution is. So you can see just by inspecting that it looks like the log normal distribution is a better fit. But we need to have a more rigorous method of analyzing the goodness of fit in a way which is not only based on intuition. So a test which is used for this purpose is the chi-square test, and this was devised by Carl Pearson, and the idea is that we take the difference, the squared difference of the observed value and the estimated value, and we normalize it by the estimated value, and we take a sum of this for all the histogram bins or for all the intervals. And then if the value is very large, this determination of if it is very large or if it's not very large is done on the basis of degrees of freedom and on the confidence level that we devise. And we are going to see this in an example, but for now you can compare the two distributions. The observed or the empirical distribution is shown in the form of a histogram, and the theoretical distribution from which we hypothesize that this empirical distribution is drawn from is shown on the bottom of this slide. And if we assume that we are going to take a sample of n data values, we can simply multiply the probability of a vertical slice with the number of values we're going to draw, and this gives us the expectation of how many values do we expect that would lie in this interval. And then we can compare both these values. We can compare the observed value and the predicted value. We can take the difference of it, take the square of it, and then normalize. And then if we add it up for all the intervals, it is going to give us an indication of how good a fit is. If the fit is very good, this statistic is going to give a low value. If the fit is particularly bad, you're going to have a very high value of the chi-square statistic. And if it is very high, if it is higher than the critical value that we've devised, then we would reject the null hypothesis and we would say that these distributions are actually different. So how this thing is done, before we get to an example, let me just clarify what a chi-square distribution is. A chi-square distribution can be thought of as the sum of multiple squared normalized standard normal variates. So first of all, let me show you a standard normal variate. This is the same as the z distribution we've seen earlier. So this should look familiar. You can see the standard normal z distribution. If you take the square of this and then you sum a lot of those together, you're going to have what is known as the chi-square distribution. So let me show you how that thing is done. So if you have a single degree of freedom, the probability density function that you would have if you are summing the square of the standard normal variates is going to look like this. You would observe that this thing is not symmetric now. All the values are on the right hand side of the y-axis. This is because we're taking a square. So we can also observe that as we keep on increasing the degrees of freedom, your density function is going to change, and it is going to form a distinctly bell-shaped figure as we keep on changing the degrees of freedom. So for 5 degrees of freedom, you see that this is a right skewed distribution. As we keep on increasing the degrees of freedom, we get an idea of what our chi-square statistic would look like. And then we can ascertain if the chi-square statistic that we have for our distribution fit, if it's very high, we can see while comparing with the chi-square distribution for the degrees of freedom that we have in our data and also for our confidence level. So an important point that I would like to reiterate is the idea of the critical region, the region in which you would be rejecting the null hypothesis. In this case, the null hypothesis is that the data follows the specified distribution, and the alternative hypothesis is that the data does not follow the specified distribution. So you would have a critical value, and on the right hand side of that you would have a rejection region, and in the rejection region you would have an area of alpha. If you have a very extreme value, you can see if it falls on the rejection region, and then you can decide if you want to reject the null hypothesis or you would fail to reject the null hypothesis. Let me give you an example which would illustrate this. So in an earlier session we have had an example from cricket. So let's now have an example from football. So let us consider data from 4 World Cups. The World Cup in 1990, 94, 98 and 2002. So this data is actually freely available, and we have data about when the goals were scored and how much of a duration interval do we have between successive goals. We want to see if we can abstract away all this data into a distribution which can measure, for example, the inter-goal duration, or it can abstract the number of goals you have in every match. So all in all, in these 4 World Cups, you've had 232 games and 575 goals were scored. So from that we can calculate the average value. So let us now think of fitting a distribution to this. So the first thing that we can do is we can draw a histogram of the thing we're trying to model. So if we are trying to model the time between goals, you can see the histogram here. And this has a distinctly exponential distribution shape. And we hypothesize that this thing would actually be a sample from an exponential distribution. We're going to cover in a future session that exponential distribution has the property of memorylessness. So we will get that later on in this course. For now, we want to see if our predicted hypothesized distribution actually matches with data. So in this graph, you can see the actual time between goals plotted against the expected time between goals if we assume the exponential distribution. So just eyeballing this graph helps us understand that the chances are good that we would have a good fit, because it seems that the two distributions are quite close together. But how good is this fit? So for that we would do a chi-square test, and the formula is shown. We would calculate the value of the chi-square statistic, and if that statistic value is very high, it would indicate that you have a lot of discrepancy. If this chi-square statistic value is less, that would indicate a good fit. That would indicate that we would fail to reject the null hypothesis. So let me show you how we can go about calculating this. So in this table, you have all the duration intervals, and it is shown that how many actual goals you had in those intervals and what were the predicted number of goals. So when we compare them, we see a good match. But we can use the chi-square statistic formula to calculate formally the value of our test statistic. And the value comes out to be 17.28 with 13 degrees of freedom. Now the question is this 17.28 less or more? Should we reject or should we fail to reject? This thing has to be understood in the context of the chi-square distribution. So we look up a table of chi-square distribution with 13 degrees of freedom, and we find that the p-value associated with this chi-square statistic is 0.19. In other words, if the null hypothesis is true, how extreme is the data value that we had? So we get a p-value of 0.19, which is not sufficient for rejecting the null hypothesis. So we would say that we would fail to reject that this data is not from the exponential distribution, giving us evidence that the goals data is actually from the exponential distribution, or it may be approximated from the exponential distribution. It's important to realize that exponential distribution is not the real cause of these goals. It's just an approximation, an abstracted model. And we must remember not to confuse the data that we have with the abstractions that we use to study those data. So let me now conclude this lecture. And in this lecture, we've seen that performance evaluation is critically dependent on the selection of workload. So this workload should be decided such that the model that we have is actually representative of the actual workload that the system would be subjected to. Also, the workload that we select must be validated against actual measurements. And lastly, I would reiterate that we should not confuse the data with the models that we use to approximate them. Distribution fitting does not tell us that the real cause of the occurrences of that is the model that we have. So I would conclude the lecture now. I'll see you next time, inshallah. Assalamu alaikum.